factories be like a few years from now? Let's see the future of industrial production. Here's a production site in the near future. Secure, private, 5G-based campus networks have speeded up manufacturing, making it more flexible, more productive, and safer. Moving further ahead, we see humans and robots working side by side. Industrial 5G paves the way for new manufacturing use cases. For instance, that cobot has a digital twin that communicates via OPC UA in an industrial 5G network. Together with various apps, these things are greatly speeding up digitalized production. Thanks to digitalization, orders are produced when and as needed. Systems will autonomously talk to each other in real time. We're only at the beginning of an incredibly promising path into the future of production. All this is future-proof and upgradable. 6G enhancements also dovetail seamlessly. Those who invest in industrial 5G now are well on their way to having the latest capabilities as early adopters. The factory of the future, connected for a circular economy. Invest in industrial 5G today and start turning this future into reality.
So good morning to everybody in the audience. I hope you can hear me fine. If so, just write me a quick message in the chat. Should work though. We tested the technique before. Okay, I see Tina saying yes. So I will present myself shortly. My name is Andrea Daquino. I work for Infineon as manager for technical standardization and industry associations. But today I'm here with the head of chair of the working group number 4 of 5G-ACIA, which is the working group in charge of liaisons and marketing. I want to take just 2 seconds of your time to thank Tina for organizing this series of webinars. The first one will be on industrial 5G devices. The second one will be on industrial 5G edge computing. Before we start, a couple of informations for housekeeping. There will be a Q&A session that you might need to use. In order to do so, please write your question in the chat on the right-hand side. Should any of the question not be answered in time, of course, you're welcome to become a member and get in touch with our presenters as well as all the other people that belong to the association. This webinar will be recorded and will be made available afterwards on the website, and everybody is going to be muted as per default, and you will not be able to unmute yourself. If you have any technical issues, then please write it in the chat again or contact our office at info@5g-acia.org. Also, we will launch a couple of polls during the presentation, and we will start actually right now. And you should be able to see the polls either in the chat or as a pop-up. So please participate, and we'll start with the first one. Which stakeholder group do you belong to? I'll give you a quick minute to answer to this. So far, 7 replies. We have 40 people in the audience, so again, a little more time. Okay, we have 11 responses. I think in order to, for the sake of time, we will then go to the next one. And perhaps if you don't see the results, we can show them afterwards at the end. The second one is which region do you come from? Still see responses coming up. Okay, I guess we can go on. And without further ado, I am honored to introduce you to Dr. Jens Jakobsen, HMS Networks. Jens, the stage is yours. I'll stop sharing.
Good morning, everybody. Thank you very much, Andrea. I will just share from my end. I hope you all see my presentation now.
Yes.
Okay, so very, very good. Thank you very much, Andrea. My name is Jens Jakobsen. I'm with HMS Networks, and I'll be presenting the industrial 5G devices, architecture, and capabilities. It's based on a white paper we wrote within 5G-ACIA, where I had the honor of being the rapporteur. I'll give you a link to the white paper at the end of the presentation. So there's a lot of aspects which are relevant when designing 5G devices, but during this presentation, I will focus on the aspects that make industrial 5G devices different from other 5G devices. So this white paper, which is basis for this presentation, was created by a working group within 5G-ACIA. So one of the nice things about 5G-ACIA is that you get together a lot of companies, both from telecom and industrial production, and then you sit down and you make discussions and you try to find solutions to the challenge of introducing 5G into industrial production. So in case of the industrial 5G devices working group, we had 28 drafting sessions or meetings with 17 major contributors and a lot of smaller contributors as well. So it was a lot of work, and we got to hear a lot of different aspects that were relevant for industrial 5G devices. Oh, sorry. Let's see, I'm back on track here. Yeah. So one thing we discussed quite early within the working group was what is actually a industrial 5G device, because when you look at a factory and you see machines that have built-in 5G devices, it would become a very, very big task if all machines should be considered industrial 5G devices. So the definition we made, and this is of course also clear from the rest of the presentation, is that if you have a machine, then it's not the whole machine that's the industrial 5G device. It's the gateway or the function specifically dedicated to industrial 5G that's inside the machine that we consider the industrial 5G device. So in order to get some clarity, we did a survey and we asked our members what kind of devices do you think are industrial 5G devices, and we then categorized them into 7 different device types. So the first type is sensors actuators that require low latency. And here we have some examples of what they could look like from Weidmüller, Fraunhofer, and Festo. So these are devices that are typically used within industrial production. We also have other devices that are sensors actuators, but in this case, it's more low power. So these are typically battery operated. One example is a level sensor. So you put the level sensor on top of the tank, and then the level sensor will give you the reading of the tank level, maybe 1 time per day or 1 time per hour, something like this. So the function is kind of the same. It's both sensors actuators, but on one hand, we have focus on low latency. This is then higher power consumption. And then on the other side, with the low power sensor actuators, the focus is not so much on low latency, it's more on low power. Then we have a quite large group of different gateways and what we call TSN ports. So these are devices that form a gateway function where you have a gateway that connects to an industrial 5G network, and then on the other side it connects typically with a wired connection to an industrial device. And here we can see different types of gateways, one from Hauser for process control. We have more process control from Kovác. We have from my own company, HMS, some gateways that one is a router, another one is like a bridge for connecting a PLC or an ADV. And we also have some examples from SIG. Then we have the range where we have HMI or extended reality. So we can envision smart glasses that are used within industrial production, or maybe something like a tablet that connects to the industrial 5G network. Also, we see examples of controllers or PLCs. This example here is from Kovác. And then finally, we have a section with 2 and 3D sensors. In this example here, we show a drone that has a built-in camera from ABB. So if we look at the market today, we see mostly gateway type of devices used in industrial production. And this is probably not surprising, because when you have a gateway, you can take an existing industrial wire device connected to the gateway, and then it can connect to the industrial 5G network. And then later on, as the technology matures, you can get more and more devices that have integrated 5G directly. So with the gateway function, you can actually perform the gateway functionality at different protocol layers. So one example is that you have the 5G network connecting using IP. And then on the wired side, you have IP as well. So this is what we typically call a IP router. You also have the possibility with 5G to use Ethernet directly on 5G. So in this case, you can make a bridge between Ethernet on 5G and Ethernet on the wired side. But also with the industrial protocols, you can have gateway functions at different layers. So the example here is a Modbus gateway. So we have Modbus TCP on the 5G network. So it uses Modbus application layer, it uses TCP, IP, and then that runs on the 5G network. But then we have a gateway function that transfers the Modbus application layer onto Modbus RTU, which runs on a serial connection, which could be RS-232 or RS-485. And finally, we can also have gateway functions between totally different kinds of industrial protocols. So in this case here, we show Ethernet IP with a temperature value operating on 5G. And then on the wire side, we have Profibus. And in this case, it's just the actual value of the temperature that we are transferring between the wire side and the 5G side. So one thing that is radically different on industrial 5G devices compared to other 5G devices is time synchronization. So time synchronization is very important within industrial production and other industrial areas. And typically we talk about 2 different types of time synchronization. We have something we call the global time domain. So this is also sometimes called the wall clock. So this is used to timestamp things within the factory. So it could be diagnostics data. So if you have an error, for example, then you want to know exactly where the error happened first, because often there's a lot of other things happening as a consequence of the error. It can also be stamping of when things are produced and so on. So this is like the normal time that we use to timestamp things within the industrial production. Then we have what we call the working clock domain. So this is used for control of the sensors and actuators by the PLC. So within the machine, everything needs to be tightly synchronized. So every cycle time, you read all actuators and you do some calculations, and then you update the values to the sensors. And this can be either the communication from the PLC to the sensors actuators can be, for example, precision time protocol, but it could also be implicit with the read and write commands received from the PLC. So the way it works on 5G is that actually the 5G base station has a quite accurate time synchronization, and this is transferred to what we call the user entity. So the user entity is kind of like the 5G function within the industrial 5G device. So it consists of the mobile equipment, the mobile termination, and of course the universal subscriber identity module. And this function receives time synchronization from the 5G network. So we get a time reference that has an accuracy that can be better than 1 microsecond. And then the UE can transfer this information to the application inside the industrial 5G device, and then the application can have time accurate synchronization down to 1 microsecond while it interacts with peripherals connected to the industrial 5G device. If we go into the case of TSN on 5G, it becomes a little bit more complicated, because with the time synchronized networks, with time sensitive networks, or TSN, you put together the 5G network and the 5G devices, and then they form a logical TSN bridge. So it means that to the outside, it looks like a normal TSN-enabled LAN switch, but on the inside, there's a lot of things happening with regards to time synchronization and also to quality of service. And inside the industrial 5G device, we once again have the time reference received from the base station. It goes to the user entity. Then the user entity will send the time reference both to the applications using some kind of time management function, but it also goes to a function responsible for IP forwarding or Ethernet bridging that we call the device-side TSN translator. So this is the one that does the time synchronization functions relevant for 5G. And then this TSN translator can then send the time reference onto the local network. So it means that using this approach here, we can get very accurate time reference on the locally wired industrial network. One challenge with this is that the protocols we normally use within the industrial 5G device can be USB or PCI Express or maybe serial communication, but those protocols are not accurate enough when it comes to time synchronization. So in order to have accurate time synchronization down to 1 microsecond and better, we need dedicated time synchronization interfaces. So this is typically a one-wire signal in the form of a GPIO that's used to transfer the exact clock synchronization. Sometimes this is referred to as a 1 pulse per second interface. So if we put this together, we see once again that we get the time synchronization from the base station. It goes into the user entity. Then typically the device-side TSN translator is inside a separate CPU. So we need to transfer the accurate time reference from the user entity to the CPU. So typically this is a digital signal in the form of a GPIO that we call a 1 pulse per second. And this is transferring the accurate time synchronization from the user entity onto the CPU, where we have the device-side TSN translator. And then on the device-side TSN translator uses this time reference to calculate the IEEE 1588 residual time between the device-side translator and the network-side translator. So then we have the wired interface. So this is normal TSN implementation. In order to have accurate time synchronization, we need to know when the PHY sends out the Ethernet frame. So this information is once again transferred from the Ethernet PHY to the CPU. So once you have those two pieces of hardware in place, like the startup frame indication support from the Ethernet PHY to the CPU, and the 1 pulse per second signal between the radio module and the CPU, we can implement the time synchronization needed for time-sensitive networks. Another aspect which is radically different for industrial 5G devices compared to other 5G devices is authentication. So if we look at the traditional SIM, we see that typically the SIM goes into the industrial 5G device using a SIM card reader. So the proper term for this is UICC, and it's put into a UICC reader. So of course, this is a challenge because quite often we want the industrial 5G devices to have an IP rating of 67 or better. So it's a challenge with this opening for the SIM card reader. In terms of provisioning, the way you do it is that you have a credential generator. It goes into the UICC, stored there as a shared secret. And then that shared secret is also stored in the 5G network. We also have the case of eSIM. So the way this is implemented is that you have a solder in UICC inside the industrial 5G device. So this is nice because now you don't have the opening, so it's easier to make a waterproof industrial 5G device. So the way it works in terms of provisioning is that you set up a PKI infrastructure. Then both the credentials generator and the 5G network participate in this credentials or this public key infrastructure. Then the credentials generator sends an EID to the EUICC. And then once you put the EUICC in the field, you can transfer the USIM credentials from the 5G network to the EUICC using this public key infrastructure. So this is very attractive, of course, because you get rid of the physical SIM card reader. But unfortunately, the public key infrastructure is run by the DSM Association, and currently it's only available to members of the DSM Association. So it's hard to apply this PKI infrastructure to private 5G networks at the moment. But then we have another option as well, and this is actually part of the 5G standards. It's possible to use authentication without the UICC. So in this case, we have a secure element inside the industrial 5G device, and then we can use extensible authentication protocol methods to authenticate the device. And when we look inside the industrial 5G device, the way it works is that we still have the user entity. It could have a USIM used for normal authentication, but then we have a new EIP identity function, which can then store credentials that are not based on USIM. So somebody will have to come up with a way to store these other identities and how to use them for authentication and so on. But at least the 5G standards, they have the support for this, but they don't define in details how the authentication mechanism should be working. Finally, we come to physical implementation options. So when you implement industrial 5G devices, you first have to consider whether you want to use a chipset or you want to use a radio module. And typical for industrial 5G devices, you go with a radio module because to use a chipset, it's a lot of work, both in terms of implementation and calibration and certification. So usually the chipset is relevant if you have a volume that's around 1 million devices or above. So usually for industrial 5G devices, you use a ready-made and pre-certified radio module. The second choice you need to consider is what form factor of the radio module you want to use. So one option is to use a plug-in radio module that plugs into a socket. It could be in the form of an M2 radio module. So this is very easy because it allows you to easily change between different radio modules. The other option, which is better suited for higher volume, is a solder-in radio module. But then, of course, you don't have the option of changing the radio module so easily. Also, you have to decide if you want to put a dedicated application processor on your industrial 5G devices, or if you want to use an application processor inside the 5G radio module. So this is, again, is a trade-off between different parameters. What is the volume? Because the application processor integrated into the 5G radio module is more optimal from a hardware perspective. But on the other hand, if you use an external CPU, it's easier to reuse the software you already have created for other industrial devices. And then finally, if you use a separate CPU, you have different options in terms of the interface between the radio module and the CPU. So this could be UART, USB-C, USB 2, USB 3, PCI Express, which are some of the common ones. And this depends a little bit on the speed and the timing requirements, but it also impacts the cost and the power consumption. So to conclude my talk today, I will say that we have 4 major takeaways. One is that industrial 5G devices need to withstand tough environments. So you need to consider temperature, humidity, vibration, and explosion atmospheres. Also, real-time communications and time synchronization require dedicated hardware. So you need to take this into account when you make the hardware design of your industrial 5G device. Also, the provisioning and authentication scenario is new for private networks. It's not the same as what you have on public networks. So this is different both from a hardware perspective, but also from an operational perspective. And then finally, I encourage you to go and have a look at our white paper, which is available at 5G-ACIA.org, or you have a little bit more detailed link on the page here. So thank you very much for listening.
Thank you, Jens, for sharing the presentation, and a very nice mascot you have there. That being said, I will share again my screen for a second, as I will present to you Mr. Benedek Kovác, working at Ericsson, and present to you the next topic on industrial 5G edge computing. Benedek.
Yes, thank you. So I start sharing. Let me know, please, if you see my sharing.
Yes.
Great. Okay. So welcome, everyone. My name is Benedek Kovác from Ericsson. And I am basing this presentation on our previous white paper, which we created as part of the work at 5G-ACIA, which is about industrial 5G edge computing, use cases, architecture, and deployment aspects. So first of all, let's start with some kind of introduction. What are those edge computing use cases that we are talking about? And before even going there, often people ask me, what's the definition of edge computing? So we started the work with asking ourselves as well, what is the definition of edge computing? How to define the best edge computing? And we said that probably it's not a definition what we need, it's probably a motivation what we are looking for. So we tried to understand what motivates the discussion around edge computing. So we came up with, on the left-hand side, a couple of potential motivations for edge computing, and on the right-hand side, a couple of locations where this edge computing could be realized. So if we start on the left-hand side, what are those motivations that motivate edge computing in the manufacturing and process industry? One is the low latency use cases. Of course, that's what everybody talks about firsthand. But secondhand, it's also the high wireless bandwidth application, aggregation of sensor data on site because of some reasons. Probably this data should not leave the site, etc. Compute intensive processes and controls, so like digital twin, XR, VR, offloading for lockup compute for optimization reasons, and application of data privacy. So one thing that we have identified is that these motivators sometimes does not necessarily require on-site or edge computing, but might motivate from a network optimization, from a use case deployment optimization perspective. In the left bottom corner, you see an overview of the edge system or the 5G system, and that shows you the mobile device on the left-hand side. So there could be application functions and network functions on top of the device operating system. And then there are several edge locations which might have different edge runtime infrastructures, cloud infrastructures, or bare metal infrastructures. And on top of them, you would have the network functions and application functions. And on the top of the whole thing, there would be a management layer. So this is the kind of abstract figure that we use to understand and try to systemize the work around edge computing. On the right-hand side, you see typical locations of edge computing. What we have identified is that there is no one definition of edge, but maybe we can differentiate among a couple of locations. One is the on-premise edge, which is very much in the site, and usually this edge infrastructure is very much owned by those who own the site as well. Then there is the public edge, which is often offered by a public edge cloud service provider, which is typically located outside of the premises. And this could be hosted in a nearby hyperscale cloud infrastructure or in a telco cloud edge infrastructure. It usually supports the multi-tenancy. So that's a big differentiator from on-premise edge, because there might be different companies using the same public edge. Then there is private edge, which is very similar to public edge, but then the multi-tenancy is removed, and it is supporting isolation and different public LAN mobile network integrated private network configurations. And then there is the telco edge, which might use infrastructure from telecommunication operators, if not with partnership with other hyperscale cloud providers or third-party brand vendors, both for private and public edge usage. This is also showing a little bit of distance from the device, not necessary, but on-premise edge is usually the closest, and then telco edge is usually the further. So when we investigated use cases, we started to collect the use cases from different sources, from different standard sources, from different projects that has been run by governments, EU or other innovation projects. And we started to categorize these use cases. What are the typical requirements of the use cases? On the left-hand side, you see a couple of categories that we came up with, and in the middle, a couple of example use cases. Like for factory automation, there are a couple of use cases which can be categorized to this category: mobile robots, collaborative robots, automated guided vehicle control, etc. But same way, digital twin operation and automated feedback is also, because we have investigated the use cases and they require fairly similar typical requirements. So for the factory automation use cases, you see the low latency for control is typically lower than 20 milliseconds and typically requires high availability. The process automation, it's even a lower latency use cases and even higher availability. And sometimes it's a high bandwidth for aggregation use cases as well. Then there is a human-machine interface, which is yet again a completely different setup. And in this case, a human is involved. So basically in the control loop, you have a human that has to interact. In some cases, this is requiring local processing and storage. In other cases, it requires low latency, like even below 5 millisecond latency, especially for the security use cases. And then when it's digital twin assisted human-based inspections, it would require the reliable communication. And then there are less latency and reliability, or less latency critical, use cases, which is still requiring high reliability, which is the logistics and warehouse automation use cases. And basically, this is important because, or reliability is important because the accessibility of the certain assets has to be done, has to be there at any time. The basic essence of the use case is to improve the current asset tracking capabilities and the accuracy of finding certain assets and products. And the last but not least is monitoring and maintenance. These are usually high bandwidth use cases, which might require local processing for data sensitivity, data privacy, sovereignty reasons. So there are typical requirements, but these typical requirements come from many different sources. On the right-hand side, there is a small figure on the bottom about the different closed loops. So what we have identified is that these kind of use cases are coming with multiple requirements on how closed the loop is, how critical the latency is. So therefore, there are different components of such applications that might at the end of the day construct the complete factory automation application. So what we did is we tried to map this kind of use cases from the group, the requirements perspective, group the use cases and try to identify what are the best possible locations for these kind of use cases. And without going into very much into the details. So I think the main point here is to understand the idea. The idea is that there are the use cases which has certain requirements, and then these requirements motivate edge computing locations. So what we did when we started the grouping is that we tried to understand which use case motivates which edge computing location. So for example, what you see here is that the closed loop control and mobile robots and evolved collaborative robots, they would require the on-premise edge cloud for sure, because this on-premise edge cloud is the only option that gives the benefit of data sovereignty and also the necessary security and others. Then the group case use cases number 2 are actually similar use cases, but they doesn't require that kind of latency sensitivity. They require latency sensitivity, but in a different sense. Here, the main difference from use case 1 is that they are covering multiple domains. So whereas the group 1 is for a single production domain, group 2 might be understood as something which is use cases between multiple production domains. So for example, if you have even multiple locations or multiple setups, then you would still have these use cases. And you would have like a centralized entity that is doing video surveillance, which means that it could be centralized to a single on-premise location, but that on-premise location might not be local to all of the factory sites. So that is the big difference between group number 1 and group number 2. While group number 1 is the single domain and the group number 2 is the multi-domain. Which means that there would be a requirement of connecting this type of on-premise clouds. And then the third use case group is the use case group which does not require this on-premise cloud. And you will see in our analysis, we did the deployment option analysis, that there are several deployment options to be considered when considering deployment of such use cases. So let's see the deployment considerations. In our white paper, you can actually find the deployment considerations for multiple of these use cases. And this is just one deployment option consideration, which I have brought up to you here in this presentation. So in this case, the use case is the closed loop control. And then this closed loop control has different requirements and different components. These different components in order to realize this use case in this example is the radio access network component, the RAN, the user plane component, which is actually responsible for the IP point of presence, the control plane component, which is controlling the networking, and the edge application itself, which is performing the task, which is giving the useful production. You see that many of these functions, like run, user plane function, and the edge application, need to be deployed locally and need to be deployed locally with the devices in order to provide the necessary low latency, data privacy, and etc. requirements, while the control plane options, which is marked in green, can be deployed at multiple different locations. So actually, it is also acceptable to have it outside of the premises because it's only controlling what is happening in the user plane, does not interact with the data itself, does not interact with the application functionality itself. So it is one of the learnings that there are different deployment options for the same use case. And of course, there could be other motivations than technical motivations when it comes to the consideration of the different deployment options. Let's move on to a next example. In this next example, we see different deployment options for placing the telecommunication functions and the application functions when it comes to the mobile robots use case. This mobile robots use case is in itself a very complex use case. Here again, the notation is that the white boxes are those which are requiring the ultra low latency, reliability, and therefore locality. So they have to be located there. And the greens are more the optional ones. And you see that there is multiple trajectory planning white boxes as well. This is also because there are different mobile robot use cases. Some of the mobile robots are very local. As we have discussed, they might be only applicable for a single OT production domain, let's say next to a conveyor belt, while there are others which are like the automated guided vehicles and others, which might move the different assets between these conveyor belts, so they might be needed to be deployed at a higher level. So that's why we have the two different edge locations, the one which is a single domain edge location and one which is a multiple domain edge location. And depending on the actual use case and the actual robot itself, we need to have deployment at different places. Here you also see a special user plane which is supporting the ultra reliable low latency communication. So it is also the case that some of the user plane functions which are serving very latency critical and very reliability critical use cases might require specific user plane. However, control plane is also more relaxed. When it comes to the control plane, you see that there are several green options and one white option in the middle. This white option of control plane, we found it important because when we analyze the reliability measures of the use cases, it has turned out that some of the requirements might require the availability and the reliability, which requires that you have a local control plane, because the link between the local center and then a centralized control plane could be also severe, which could also introduce new reliability conditions. Yet again, this is just done for example use cases and example calculations, so that might not be true for all of them. But this is mainly the method how this could be calculated, and what we have investigated is that what use cases are required how do they motivate edge computing, what type of edge computing they motivate, and at the end of the day, if the deployment of such edge computing use case using the different options is actually possible. So maybe one other thing to highlight on this figure is the exposure function. We have also understood that sometimes the application, like the fleet control application, needs to interact with the network, needs to require new data channels and etc., or needs to require quality of service considerations. In this case, it has to interact with the network. So we have put here the green exposure boxes that at some point there has to be a network exposure capability, which can be used to control the network using the APIs, create new data channels, or get notifications on the change in data channels. And that also draws us to one more conclusion, which says that sometimes it is the dependency between the network functions that also requires the different deployment options. Let's go for our last example. In this last example, we have the different user plane function deployment options. This user plane function is important, we have talked about, because this is basically giving the basic service of the network, that is IP or LAN capabilities. And depending on how the use cases would like to be deployed, there are multiple deployment options. On the left-hand side, all the edge platforms are accessible by the user plane function. And these edge platforms then at the end of the day collect the wired functionalities as well, and then can connect the wired with the wireless. In the right-hand side, there is another option to use the 3GPP trusted non-3GPP gateway function, which can integrate wired functionality into the UPF. So basically, all the wired devices will be handled with the same user plane function and the same policies that it implements as the wireless ones. So whereas on the right-hand side, the wireless world is a bit more isolated from the wired world, on the right-hand side, a bit more integration is done. Yet again, this is not a requirement, none of them. Both of them are options, and options of deploying the edge computing use cases. With this, I would like to come to the conclusions of my presentation. First point, 3GPP addresses the general requirements for implementing and deploying the use cases in terms of networking and communication. So there are capabilities in 3GPP already existing, which is enabling most of the use cases, and implementation can be started. And then there are standard capabilities which are either planned or existing for implementing this networking and anticipated edge computing use cases, which means that if there is something which is missing, like the ultra-reliable low latency communication is just under development and discussions, or some other capabilities, they are also planned and on the way. 3GPP also offers the flexibilities to select the optimal deployment model, and I think that was one of the main conclusions that we came up with. There is no one size fits all. There is no one solution fits all. There are different flexibilities and different deployment options, which has to be engineered for the given use case. There can be recommendations, as we have done or in our examples. However, these are not carved in stone, and there can be other considerations than the technical considerations, like economic considerations. And please check out our white paper. So in further details, you can find on the 5G-ACIA webpage. Thank you very much for listening to my presentations.
And thank you, Benedek. I'll take control of the screen sharing again for the Q&A session. There was one question for Jens, which is, are there any commercially available industrial 5G devices which realize the 5G clock interface?
Yes, it's a very good question. Thanks for asking. As far as I know, there's no commercially available devices which does this kind of clock synchronization at the moment. From our own perspective, we have this implemented in hardware, but we do not have it commercially available yet because we have not been able to test with infrastructure and our own software yet. Also, from a use case perspective, the use cases we are discussing with our partners now are not so much within industrial production. It's more within mission critical infrastructure for public safety, where you cannot rely on the time synchronization that you are provided from a DPS from a reliability perspective. So in this case, time synchronization from the 5G network is a valid alternative. But I think we are a little bit too early for commercial devices yet, but it will come in the near future.
And thanks, Jens. Then I'll play the devil's advocate for a bit and ask a question to Benedek about edge computing. I was wondering, does edge computing even make sense with older cellular technologies such as LTE or even UMTS?
Yes, I think the short answer is yes, and the reason is because it is not necessarily the cellular technology that actually defines the benefit of edge computing. Sometimes it comes from the sheer fact that the data has to be kept locally at the factory. So data sovereignty and the data sensitivity is actually one aspect where edge computing discussions start to pop up. It's not even if it's a 5G, 4G, or any other type of connectivity that is deployed at the radio access part.
Then a follow-up question will be, what are the advantages of using 5G in this kind of architecture?
In this kind of architecture, 5G gives us the capability of network programmability, of quality of service. So if we are using the 5G or even the 4G access technologies, the 5G core network and the 5G exposure technologies gives the capability of the industrial applications to interact with the network in a standardized way, using the different network APIs and using the exposure interfaces. Which is not possible with other technologies.
Okay, thanks very much. There is another question for Jens. Is RedCap relevant for industrial 5G devices? How's the RedCap status now? Any commercial use cases?
Yeah, so actually this is also a very, very good question. And we had this on the display on the demo wall that was last seen in Shanghai. I think it was a couple of months ago. There were some industrial devices using RedCap. And I think with the ordinary 5G devices, you get very, very low latency, you get high speed and so on. But in many applications, you don't need gigabit speed, because if you have a sensor actuator, it's usually only a couple of hundred kilobits per second. And if you look at an ATV application, for example, it usually gets an update every 10 meters, and so telling it where to go for the next distance. So there's a lot of applications. Well, of course, there's a lot of applications within industry that requires low latency and high bandwidth. But there's also a lot of applications that can live with the couple of 100 megabits per second that you can achieve with the RedCap. And there's a couple of advantages with the RedCap. One advantage, of course, is that the price of the radio module is significantly cheaper. So this is one aspect. But the other aspect, which is also quite important, is that with the ordinary 5G devices, you have a requirement to use 4 antennas. So it means that the devices, if you have built-in antennas, they become bigger, or you need to place 4 antennas on your ATV or other machine that you have in the factory. But with RedCap, you can get away with having only 1 or 2 antennas. So it means that we can get the form factor down, and this again, it opens more use cases within industrial automation.
Thank you very much. And before we take one last question, I would just point out that Jackie sent a couple of links in the chat. So one is for the next webinar coming next week. One is for past webinars on our website. And the last one is to follow 5G-ACIA on LinkedIn, which would be also the last slide that I want to mention. But before I close this webinar, I would actually want to do one last question for Benedek. What is your view combining edge computing via MEC and 5G slicing for industrial use cases?
I have not emphasized that in this presentation, but network slicing it's one of the technologies that can enable a lot of different implementations for edge computing use cases. So basically what we see on the different use cases in a factory environment, starting from production towards AGVs and then video surveillance, human interactions, and then just simply data analytics, they might be requiring different network slices. These different network slices might have different network functions in them. For example, for the ultra-reliable low latency slice, the UPF might be a different instance than for the video surveillance data collection slice, because there are different requirements for such UPF. So, and also the concern of interference between the two applications require the most separation. And network slicing is a great technique for doing that. So the question is, yet again, very easily, yes, it should be combined.
Thank you very much again for the answer. And with that being said, I don't see any more questions in the chat. Perhaps Tina's question can be answered directly by writing at info at 5G-ACIA.org. And there is also a compliment from Mr. Persico. Thank you for the interesting seminar. Well, thank you for the attendance. And yeah, I'll see you at the next series of webinar next week. Thanks again to everybody and have a good day.
Thank you.
Thank you.
Thank you. Bye.